welcome to the second part of our energy efficiency crash course. So if you watched the last video, you'll remember that in part one, we talked about what energy is, the law of conservation of energy, and energy transfers and transformations. And in this video, which is also intended for secondary 4 students, we're going to talk about energy efficiency, which is super relevant and practical in everyday life. So we're going to talk about what the definition is of energy efficiency, the different formulas. So there's one formula where we're going to learn how to manipulate the formula, and then a couple of examples to see how you do with practice. So before we start getting into any of the formulas, we need to understand what energy efficiency is. And energy efficiency is a percentage of consumed energy that is transformed into useful energy. We always want to be efficient. We want to be efficient in how we work. We want to work harder or smarter, not harder. We want to make sure that we are efficient in all things that we do. And the same thing goes for any type of system. We want it to be as efficient as possible so that we get the most bang for our buck. So consumed energy is something we need to understand as well, because that's in the definition. And that is the energy input of a machine or system. So what the energy or the system consumes, it's its input. We have useful energy, and that is the energy output of a machine or a system that corresponds to the desired task, whether that be washing clothes or turning on a light. This is our formula. So it might look a little scary at first, but don't worry, we're going to go through it all. Energy efficiency, which we also use as EE, is equal to the energy that is useful divided by consumed energy times 100, because remember, energy efficiency is measured in percentage. Now remember, in the last video, I said that energy is measured in joules. So it's a capital J as a unit of measurement. And remember that our energy, our final energy efficiency, is always going to be measured in a percentage. So let's have a look at what this looks like in real life. So when we talk about energy efficiency, often we like to talk about cars. So right here, I have a gas-fueled car and an electrical-fueled car. And so we're going to talk about how that works for energy efficiency. So for example, if you had a question, you have a gas-powered car that consumes 1,000 joules of chemical energy, because remember, gas is a fossil fuel, it's chemical. It transforms 150 joules into mechanical energy. So if we plug those two values into our energy efficiency formula, we get 150 joules divided by 1,000 joules times 100, because remember, energy efficiency's unit of measurement is percentage. So we see that this car is 15% efficient. So what does that mean? It means that 85% of the energy that went into the system is not used efficiently. It dissipates. It's not lost. Remember, it can never be, energy cannot be created or destroyed, just transformed, but it dissipates. So it's not used efficiently. So this car would be also called a gas guzzler. If we look at the second car, which is an electrical car, it consumes, again, 1,000 joules of electrical energy, but it transforms 770 joules into mechanical energy, right, getting that car to work. So if we plug those values into our energy efficiency formula and times it by 100, we see that this electrical car is 77% efficient, meaning that 23% of the energy dissipates. It's not used efficiently. So if we remember, in a closed system, so this car, for example, is a closed system, we have an input and an output, the energy consumed is equal to the useful energy plus the dissipated energy. So remember, in the law of conservation of energy, nothing is created nor destroyed. It is simply transformed. So in this case, energy efficiency, we always want to have that total amount in that closed system. So before we get into any examples, I want to play around with our energy efficiency formula first. So as you can see, we have 3 variables in here. We have energy efficiency, useful energy, and consumed energy. And so we need to kind of know how to work this formula so we can solve any one of those. So as you can see, the first one that we did was energy efficiency. That's how we find it. Useful divided by consumed times by 100. So now what happens if we want to find useful energy? Well, we have to move everything over to the other side of the equal sign so that we can solve for useful energy. So we need to isolate for that useful energy variable. So the first thing that we're going to do, as you can see, is we times by 100. Well, what's the opposite of that? We're going to divide by 100, and we're going to do the same thing on the other side. So we're going to divide by 100 here. So that cancels this out. Goodbye. Then after that, so as you can see down here, we've moved it over. Then we still want that useful energy to be alone, but it's divided by consumed energy. So what's the opposite of division? we want to multiply. So we're going to move that multiplication over to the other side. So as you can see down here, we have our transformed formula. The useful energy equals energy efficiency times consumed energy divided by 100. So that's one of the formulas when you manipulate it that you can use. And if we want to find consumed energy, we can also move a couple of things around in order to solve for that variable. So again, we'll take our energy efficiency original formula, always take the original formula, and then we're going to manipulate it. So what we're going to do is we're going to say, okay, well, the only things that we need to really move around are consumed energy, because that's what we want to find. Okay, and then energy efficiency. So I'm going to take my consumed energy and I'm going to make sure that everything is isolated, or I can just move it to the other side of the equal sign. And then I'm going to take my energy efficiency and I'm going to move it down here. So again, we are just manipulating the formula. We're thinking to ourselves, okay, what's the opposite of the order of operations so that I can move it across the equal sign, bedmiss, and then we are ready to go. So let's take that energy efficiency formula and try out a couple of examples. So here's our first one. A customer works to purchase an energy efficient heater. They are given the following information about 2 models of space heaters. Which heater should the customer choose? So we have model A, which is an electrical heater, and model B, which is a gas heater. So model A has the heating elements of the heater transform 232 joules of the electrical energy it consumes into thermal energy and 48 joules into radiant energy. So that's our first choice. And then the second choice is model B. The heating elements of this gas heater transform 214 joules of the chemical energy it consumes into thermal energy and 38 joules into radiant energy. So now we need to figure out which model we're going to pick. What is the useful energy in a heater? Is it A, thermal energy, B, radiant energy, C, electrical energy, or D, chemical energy? The answer is A, thermal energy. So remember that useful energy is that energy that is used to perform a certain task. So what's the job of a heater? It's to heat a space. So thermal energy is what we're looking for. So the first thing that we need to do in a question, in any type of example, is look at what we're given and write down what we're given. So in this question, we have our useful energy, our consumed energy, and our energy efficiency that we have to look for. So in the question, we look at our useful energy. So the heating element of this heating transforms 232 joules of electrical energy. That is our useful energy. So we write it down. Helps us figure it out. Then I don't have to use that value. Okay, it's done. Then after that, we have our energy consumed. And it says it in the question. It consumes into thermal energy. And remember that in a closed system, we need to add those two together. So our energy consumed, so it uses 232 plus the 48 joules of consumed energy. So we get a total of 280 joules in this system. Okay, and what are we looking for? We're looking for energy efficiency. So that's what we're trying to find here. So we're going to plug these values into our formula. Now you have to remember that our formula for energy efficiency, you always need to write it down first. Okay, it's there for you. You know where it is. You can fill it in. Okay, always write down the original formula. So if you look here, we plug in our values. So 232 joules divided by 280 joules, and we always times by 100 because energy efficiency is measured in percentages. So we're left with 83% efficiency, which isn't that bad, to be honest, for our first heater. Remember? So that means that 17% of the system dissipates, but it efficiently uses 83% of the energy. So doing the same process again for the second model, so the gas heater, we're going to look at the question again and fill in what we're given. All right, so the heating elements of a gas heater transform 214 joules. So that is my useful energy. And it consumes 38 joules plus the original 214. So we don't want to forget our units of measurement. Joules. So that gives me 252 joules of energy in this system. And we're trying to calculate energy efficiency. So again, we're going to take our original formula and we're going to plug in the values that were given in the question. So we're going to take 214 joules of energy divided by 252. times by 100 because energy efficiency is always in percentage. And so we get an answer of 85% efficiency. So the final answer to this question is the customer should choose Model B because it has a higher energy efficiency than Model A, right? 85 is more than 83. Let's jump into a second example. A new microwave model has an energy efficiency of 72%. I would underline that. Determine the amount of energy used to heat up food it consumes if it consumes 16,450 joules of electrical energy. So look at the vocabulary here. We know energy efficiency. We can write down what we know, right? Because we're looking at that formula. So we have 72%. That is what's mentioned to us in the question. Determine the amount of energy used to heat up food if it consumes 16,450 joules. So it consumes 16,450 joules of energy. That's our consumed energy. We're trying to find useful energy. So again, we're going to use that formula, our energy efficiency formula, but we're going to do a little switcheroo so that we can modify it so that we can solve for useful energy. So if we do that, we take our original formula. Okay, we have energy efficiency equals useful energy divided by consumed energy times 100. We're going to move it around. So you can go back if you need to in this video to look and see how we did that. We use energy that is useful. And what we do is we make energy efficiency times consumed energy divided by 100. So we're going to put our values in. 72 times 16,450 joules divided by 100. And we get an answer of 11,844 joules of energy. So it uses 11,844 joules of energy to heat up the food. So let's take a look at one final example. The blades of a small battery-powered fan use 512 joules of mechanical energy. How much chemical energy does the fan consume if 46% of energy dissipates? So first thing you need to look at here is the vocabulary. We see 46%, but look beside it. It says energy dissipates. So it's not energy efficiency here, but it's still a percentage. So we're going to come back to that in a second. So the blades of a small battery powered use 512 joules. So if they're using 512, that's useful energy. So we're going to put 512 joules. Okay. Now, how much chemical energy does the fan consume? So we're looking for consumed energy. But we still have that 46% of energy dissipates. Now remember, in a closed system, the input and the output, you have to have that 100% in there, right? So if we take 100% of the energy that goes into a system and 46% of it dissipates, how much is left that's efficient? So that's how that works. You have energy that's used efficiently, and then you have energy that dissipates, that's not used efficiently. So if I do 100 minus 46, that gives me 54% efficiency. So that's the number that we're going to use in our formula. So if we look at our solution and we take what's given to us in the question, we're going to use energy consumed because that's what we're trying to find. So if you need to go back into this video to look at how we manipulated that formula, do so. So energy that's useful times 100 divided by energy efficiency. So I take my 512 joules of energy times 100 and divide by that 54%. So we get that the energy that's consumed by the blades of the small battery-powered fan, it uses 948 joules of energy. And there you have it. There is our complete video on how energy efficiency works and what it does. So remember, in summary, energy efficiency is the percentage of consumed energy transformed into useful energy. And remember this formula. It will most likely be given to you on an exam, but you have to know how to manipulate it. You have to know how to find useful energy and consumed energy. It's also important in any science, when we do any science math, you have to remember to put those units of measurement. So remember that useful energy and consumed energy are both measured in joules, and that energy efficiency is measured in percentage. And always, always remember that energy consumed is equal to the useful energy plus the dissipated energy in any system.